Our next speaker is Amartya Mitra, who is a grad student in physics at University of California, Riverside, and this is work he did while at Mila as a long-term intern in Montreal. And he's going to be talking about least action dynamics for min-max optimization.
Thank you, Gal. I would like to thank the organizers for giving me the opportunity to talk at Deep Math. And today I will be talking about a work that I did during my long-term internship at Mila with my collaborators Reyhane Askari, Gilm Najwa, and Yanis Mitliakis. So at the very outset of my talk, I would like to provide the main takeaway of our work. That is, in this work, we propose a novel optimization scheme for min-max games by using concepts from physics to tackle the issue of problematic rotational dynamics that is commonly encountered in this setting. The structure of my talk is organized as follows. Well, firstly, I will argue as to the case to study min-max games, and then I'll describe in detail as to what these rotational dynamics that I mentioned of are, and then briefly overview some recent efforts to alleviate this particular problem, and then propose a different way of approaching this line of issue by using tools from physics. Using this physical setup, I'll then demonstrate our new, well, rather devise our new optimization scheme, which we call LEAD, and then follow up with convergence analysis of this particular method. Finally, and conclude by providing experimental results of this proposed optimizer and compare it with other other methods in this particular domain. So min-max games, which also occurred in the previous speaker's talk, are two-player games where players have competing objectives. And this is an important setup to study and understand adversarial interactions in a game, especially in the light of GAN training, where the generator tries to fool the discriminator while the latter tries to catch on the scene. So it's known that GANs are able to generate high quality realistic images from pure noise and have other wide-ranging applications. And it's pretty useful. But one particular or pressing issue in this line of work is that training GANs is actually a hard problem and thereby impacts progress. This difficulty stems from the fact that gradient-based methods, which are very successful in traditional optimization or single objective optimization problems, happen to perform poorly in this setup. Notably, they exhibit rotational dynamics, as is shown in this particular figures, around the Nash equilibrium. So Nash equilibrium here refers to the stationary points in a game where neither player can benefit by individually deviating from that particular point. So to understand a bit more in detail as to where this rotational dynamics originate from, we take a look at a specific type or simple type of min-max games, namely bilinear games. So performing gradient ascent in this particular setup actually leads to those same kind of rotational dynamics or rotations around the Nash equilibrium, which in this particular setup is situated at the origin. And these dynamics occur actually because of the following reason. In these game settings, each player have their own individual loss or objective, and which itself also inherently depends upon the other player's parameters. So performing gradient descent updates does not necessarily correspond to minimizing a single objective and thereby climb down some potential. There have been recent works which have tried to attack this particular problem, such as works by Balduzzi et al. And Mescheder et al., who propose methods like symplectic gradient adjustment and consensus optimization, which introduce second-order information in the update to tackle this problematic rotations and is able to improve on the convergence in this setting. But one issue is that they introduce this second-order information in a kind of carefully hand-designed way. So our premise, or rather the premise of our work was, is there any way of developing an efficient optimization scheme in this setting without having to handcraft a way to curb these rotations? As we will see, that concepts from physics can be used to answer this question. We will try to model min-max optimization as the dynamics of a physical system, and will then aim to leverage physical laws so as to determine a naturally efficient optimization trajectory for this setting. So some bit of physics, that is, we know of Newton's second law, which in classical mechanics, which states that mass times acceleration of an object is equal to the net force acting on the object. And this law actually determines the trajectory of this equation, determines the trajectory of motion of this object under the influence of this net force. It happens that this law can be derived from the principle of least action, variational principle, which states that a system evolves along a path along which a quantity called the action is minimized. So to make some meaning of this last statement, let's look at the following graphics. Let's say an elephant is falling down under gravity. It doesn't really fall down, right? We know that from observation. Things fall down straight, like this. Right? Oh, by the way, I'm against animal cruelty, so this depiction is purely for illustrative purposes. So going back to topic, the reason that the elephant is falling straight down is because of the fact that action is actually minimized along this linear path and not along the curved path. So in the following, we would want to evaluate what the corresponding physically preferred path would be for the case of min-max games. To do so, we actually take the following route. We first try to cast gradient descent on a min-max game as the trajectory of some physical system. We can then subsequently add appropriate counter-rotational forces. There are known physical forces that we can add to see how we can counter these rotations effectively so as to curb the rotations of the starting setup, that is by the one that models the min-max case. Once we're able to do so, we can consequently employ Newton's second law so as to determine what would be the corresponding trajectory of evolution of this resultant model setup. So it happens that gradient descent plus added momentum, which is important, in continuous time as a continuous time dynamics on the min-max game, happens to resemble the dynamics of an object moving in a vortex force. So this vortex force can be perceived to be that occurring in a whirlpool, say, and this vortex itself, the force can be constructed or is constructed from the min-max objective of our work. So under this particular force, or this vortex force, the particle, of course, still exhibits rotational motion. But now, having been able to model it as a physical system, we can introduce, as we mentioned, additional other physical forces to counter the rotations of the setup. So as a first attempt, what we do is that we consider another known physical force, which also known to exhibit rotational dynamic or having rotational effects, namely magnetic force. So this was a particular choice. A different choice can, of course, be taken. So what we did was we added magnetic force, and we also happened to add friction to our system. So this third force is somewhat more subtle. So the vortex force is known from literature to be non-conservative. It happens to pump in energy to a system. Magnetic force doesn't change the energy of a system. So there should be some other force that has to be incorporated in a physical system so as to make sure that any particle moving in it happens to settle down at a point, that is, converge. So friction is a very commonplace dissipative force. So we happen to introduce it here as a way of performing that energy dissipation. So these are the three set of forces that we consider. So firstly, again, we take the vortex force as a model of min-max as a gradient descent, and then the magnetic force acts as a counteracting force in our setup, and the friction, as I mentioned, is for energy dissipation. with these three forces in the mix, oh, by the way, there is a schematic that I happen to show. So the vortex force is actually acting, taking the particle in a circular path, and the magnetic force, its role rather, is to curve this path towards the origin, which in our case is the Nash of the min-max game. And we'll see how these forces interact. So taking these three forces, one can correspondingly write down their equations of motion as governed by Newton's law, and they take this following form. So the first term in the RHS, or right-hand side of this equation, is the vortex, it corresponds to the vortex force, which mimics the min-max gradient descent. The second and the third term correspond to those generated from the magnetic and frictional forces. Here, friction is actually taken to be velocity dependent. And just to add, the Q and mu here are the charges, the charge of the particle that we assign it, and mu corresponds to the frictional coefficient between the particle and its two-dimensional surface in which it's moving. So two-dimensional because it's two players in that regard. So having all of that, the continuous time equations in hand, what we next plan to do is discretize them for performing optimization. The discretization technique that we use is symplectic discretization, which involves using a combination of implicit and explicit Euler discretization methods, which consequently results in our novel optimization scheme, which we call LEAD. And in here, beta, eta, and alpha, the momentum coefficient, the learning rate, and the important counter-rotational hyperparameter, which decides the strength of the counter rotations, all happen to be dependent upon the mass, charge, and frictional coefficient of the starting physical system. So just as a comparison, I happen to show two other methods at the beginning of the talk, and to compare how our method looks in terms of, in regard to theirs, we notice that LEAD, our method, happens to contain an extra momentum term. And more importantly, it just depends upon the off-diagonal block of the Hessian of the game, while the other two methods involve full Hessian computations. As we will see when I will be discussing the experimental results, that this particular feature of dependency of just on the off-diagonal part of the Hessian of the game leads to significantly faster runtimes, so that are even comparable to first-order methods in this min-max game setting. So before I move on, I just want to show that the LEAD is indeed able to curtail the rotations in this min-max game setting or bilinear game setting, and ends up converging to the Nash at the origin. So moving on to convergence analysis first, we analyze the convergence behavior of our method by using Lyapunov theory from dynamical systems theory, and it works in the following manner. So in the continuous time case, the method works as follows. If one is able to show that there exists a positive definite function of the game parameters, which monotonously decreases in time over the optimization trajectory, then the particular optimization scheme is said to be convergent in that particular game. A similar kind of an argument also holds for the discrete time case or discrete time optimization path. What we happen to find is that in a specific type or specific class of min-max games, namely quadratic min-max games, which are an extension of bilinear games by having strong monotonicity. Well, there's a mistake here. It should be typo here. It's x squared minus y squared when I define the function. So in this particular class of games, we're able to show that there does exist discrete time and continuous time Lyapunov functions, or these positive definite functions possessing this particular monotonically decreasing property, and which guarantees convergence. So just to show they happen to look a bit cumbersome. Just to add a bit more detail on this convergence behavior, in this particular game setting, this class of games, that is quadratic min-max games, we are able to prove linear convergence of our method, both in continuous and discrete times. And yeah, oh, sorry about that. Oopsie. So regarding the experimental results, we performed 2 sets of experiments on GANs. The first one is image generation. The first one is generation of 8 Gaussian task, where we use the Adam optimizer as the baseline. So it is observed that while Adam suffers from mode collapse in this particular generation task, lead is able to capture all the modes, even for the non-zero sum formulation of the GANs. So to emphasize the last part, the lead optimizer was developed using a min-max formulation game, and it happens to perform well even for the non-min-max setting of this generation task. The second set of experiments that we perform are on CFAR10 using a ResNet architecture, where we again use Adam as a baseline, and it actually achieves an impressive fresh at inception distance score of 11.22, which is lower the better. And it happens to outperform the big GAN, which is about a 30 times larger architecture than ours. Some additional comparisons with other methods, namely the ones that I showed earlier in the talk, symplectic gradient adjustment and consensus optimization. Our method, lead Adam, happens to be significantly faster due to the feature that it only depends upon computing off-diagonal part of the Hessian. And it's actually comparable to several first-order methods, namely optimistic mirror descent by Daskalakis and co-authors. And it also improves upon the FID score over the SN GAN and look-ahead GANs. The SN here stands for the spectral normalization GAN, which was state-of-the-art some time back. With that, I kind of near the end of my talk. Just the final takeaways. In this method, we happen to model min-max optimization of the physical system to derive a novel optimization scheme, which we term lead. This way, we were able to curb the rotations in this min-max setting in a sort of physical way. And it actually has impressive performance in this GAN setting, and is even cheaper than several second-order methods. So yeah, that's kind of it. And a paper just happened to arrive in archives some time back, so feel free to check out. And thank you for your attention and attendance.
Great, thank you so much for that interesting perspective on GANs. We have a question from the audience. Evolution of a conservative mechanical system is symplectic. Is your method related to the SGA method through this, or is this just a coincidence? Are they operating on the same phase space, for example? You can also see the question in the chat.
So regarding this, so our method and SGA, so just to be something that I didn't particularly emphasize upon, so symplectic in the more true sense of the term implies preserving the symplectic structure, that is the Poisson brackets. That is actually not done in our case. We happen to use the term slightly loosely in the sense that using a mixture of implicit and explicit updates in our discretization, using implicit and explicit discretization schemes in formulating our discrete time optimizers. So that way we're using the term. So it's not truly symplectic. So that's something that we mention in our paper. Regarding to,
of course, it's not going to be truly symplectic anymore. The question is, if
sorry,
I asked the question. Can you hear me? Sorry.
Yeah, now we can hear you.
No,
Okay.
yeah, I can hear you.
Yeah, I was going to say that since you introduced a friction term, then of course your evolution is no longer symplectic. But if you didn't, then you were doing some kind of classical mechanics. Is this kind of,
So
then you would have a symplectic evolution? Well, I don't know. Maybe this is too detailed. We can chat about it in the
sure,
break.
absolutely. I'll be happy to. Regarding, just to quip in one more thing, is that regarding the coincidence with SGA, it's a little different than our method. And yes, it follows in, SGA is derived as minimizing over the gradient square or the L2 norm of the gradient. So it's not exactly following our technique. It's very similar to ours in appearance, but there's a slight difference in formalism. So I'll just end with that.
Okay, so we'll be taking a 12-minute break now.